Flat's so smooth you could calibrate your life choices. Six months in the making. I lost count of how many revisions. I learned electronics and designed the PCB. I taught myself Fusion 360 to build the housing. I spent countless late nights coding and testing and iterating. And then 2 months of real-world field testing. FlatAF wasn't just built, it was forged through obsessive problem solving and learning curves and an astrophotographer's refusal to compromise. What began as a side experiment to simplify flats in my backyard and on the road turned into a complete portable network integrated calibration system. It works wherever you do without the complexity or price tag of commercial options. So, disclaimer. FlatAF is a DIY, do-it-yourself project intended for educational and personal use. AstroAF does not manufacture or sell FlatAF panels and provides no warranties, guarantees, or support for third-party builds or modifications. So what is FlatAF? FlatAF is an open-source, Wi-Fi controlled flat panel system for astrophotography. It's designed to deliver reliable flat frame calibration in both backyard and mobile imaging setups. The device combines low-power LED illumination with real-time brightness control and full ASCOM Alpaca compatibility. This enables seamless automation through capture software like Nina. So unlike commercial flat panels, FlatAF is battery-powered, it's network-aware, and completely DIY from the PCB and firmware to the 3D printed housing and open API. Whether you run a minimalist field rig or a semi-permanent setup at home, FlatAF offers an adaptable, lightweight solution that integrates directly into your calibration workflow with no cables, no tether, and no guessing about brightness levels. Alright, so why did I build this? You can try to perfectly match your sensor to your scope to achieve 100% relative illumination. You can try to keep your optics spotless. You can hope the sky plays nice with you every session. You might not experience edalone or other interference phenomena in your light path. But in the real world, we don't all have the exact camera and scope combination for every setup we work with. We work with what we have, within our budgets. We can clean our optics perfectly, yet still accumulate particles overnight during a session. We have varying gradients throughout the night from changing sky glow and light pollution. This degrades our consistency of our subs. When interference patterns in your subs ruin your session, flats are necessary. So for the common astrophotographers wishing to get the best results from their efforts, from our efforts, calibration is a necessity. The origin of this project was a persistent calibration issue in my narrowband imaging workflow. Despite employing careful data acquisition and processing, I observed recurring artifacts in my integrations, particularly within the red end of the spectrum. These included visible banding, repetitive noise patterns, and characteristics that suggested the presence of edaloning. To address this, I initiated a methodical troubleshooting process. So I consulted with both the camera and filter manufacturers, and I experimented with stacking and calibration techniques, and I reviewed technical documentation to understand the mechanisms behind edalone artifacts. And through this process, I identified the cause. My twilight sky flats were not only failing to correct these issues, but were actively introducing them as well. And these inconsistencies in the spectral response, combined with uncontrolled illumination conditions, rendered the flats ineffective for precise calibration. So special thanks I'd like to give to, as a shout out to Player One Astronomy and SV Boney for their incredible support in helping me research and the assistance in diagnosing the root cause of the severe edaloning artifacts that I was having as a result of my particular image train. And it's nothing wrong particularly with my image train. It's sort of inherent, and it's in the red bands, and it is mainly caused by some internal reflections that can occur between the sensor and the backside of the filter. But what I found is that through the insights that were gained through this research and working with Player One and SV Bony, because I use the Player One camera and the SV Bony filters, their insights helped me guide the investigation that ultimately led to FlatAF being the solution to my issue through the use of highly controlled and high quality flat frames paired with matching dark flats. Okay. At this point, I did away with biases and I introduced dark flats into my workflow, and this solved so many problems for me. And I'm really grateful for the responsiveness and commitment to supporting the astrophotography community from Player One Astronomy and SV Bony. So thank you very, very much. At that point, I began evaluating alternatives. Several commercial flat panels were available, but most lacked the specific features that I required, particularly the ability to control brightness dynamically and operate wirelessly. So some existing DIY options offered partial solutions, but often relied on tethered USB or Bluetooth connections, which did not align with my goal of a fully wireless experience. Additionally, these systems often lacked a robust and open software interface. In response, I made the decision to build my own solution. I purchased a 3D printer, which you can see behind me here, mainly to fabricate the enclosure, which in the FlatAF enclosure is completely printed here. And I only have a few parts in this that were purchased as far as the enclosure was concerned in the light panel, so like the LEDs and the diffusers. I began learning electronics in order to design the supporting PCB circuitry. I also taught myself Fusion 360 to create a purpose-built housing, which I just showed you, that integrates cleanly with my existing imaging setup. The interesting thing about that is that this is designed here for the Edge HD 8 and fits the dew shield perfectly. There's a foam seal in here. This is light tight, and this housing just integrates cleanly with my existing imaging setup. So over the following months, I developed and refined both the MicroPython firmware that goes into this device, which is FlatAF, and a cross-platform ASCOM Alpaca driver. This is a Python driver, which is new in the newest Alpaca. And I just went through these iterations over and over and over again for the last 6 months, improving on this, testing, improving. And I finally come up with this, and it's at a point now where I'm releasing it to you, the community. And I hope that this will be something that you might check out and enjoy. FlatAF is the result of that process anyway. So a Wi-Fi controlled, open source, ASCOM compatible dynamic flat panel. While it began as a personal solution to a specific imaging challenge, the project quickly evolved into an opportunity to expand my own technical capabilities and learnings and contribute something back that I think is meaningful to the astrophotography community. It's fully open source. It's available on GitHub right now. The design files are available on my website right now. They link to each other, and links to those are in the description. How FlatAF works. I'm going to get into a demo here in a moment, but we can talk about this just a little bit here. So what FlatAF is, I have an enclosure here, which neodymium magnets hold the lid on. And inside, I've got a microcontroller. And that microcontroller runs on MicroPython. And I have the MicroPython FlatAF software loaded on here. And I'm currently controlling it through Nina. So when I did this previously, and I hit this and I turn it on, that's actually my mini PC connected to my telescope that's controlling this through Nina that I have here on my computer. And I'm actually about 50 or 60 feet away from that computer right now. And I'm connected to the Wi-Fi for the router that's on the telescope, and through walls here, my exterior wall, and out into the yard from here in my studio. And it just does excellent. So from a line of sight without obstructions, you probably have a good 75 to 100 feet without any problem. I could see this being something that you could take into, like if you're like traveling to a dark site and you were in a tent or in your RV or whatever, you could take this back with you, into your tent and actually turn it on and use it as your light if you wanted to. If you lost something around your telescope, you could certainly turn this on and use this as a light to help find whatever it is that you dropped in the pitch darkness. So there's auxiliary uses for this as a light that you could certainly use, and I thought it was just kind of neat, to have those options. It has a PCB enclosure. It's battery powered, so it's got a compact LiPo battery. This, in my testing, will last in standby for about 14 to 16 hours or so. It charges up quickly. It charges through a USB-C interface. And you can charge this fully charged in like an hour or so. It's pretty fast. You could plug it in for 15, 20 minutes and it would work for you for at least a couple hours. So if you needed a quick fast charge, you could do it. Compact, it's battery powered, it's Wi-Fi controlled. I added this antenna here for Wi-Fi to get better range, and it worked great because the little antenna that's built into the micro controller doesn't have a whole lot of range, but adding this, I made a big difference in extending the Wi-Fi range. And anyway, this is designed for astrophotographers who need reliable and portable calibration tools in the field or at home. It supports full ASCOM Alpaca integration for the automated capture software such as Dina, while also allowing manual control through a browser interface or via a single onboard button, which it has here. And this button is basically so that you can turn on or off the light, just as such. And then if you long press this button, it'll put it into an access point mode where you can configure for your Wi-Fi. So if you're configured at home, then you can have that set up when you go on the road and you might have a different Wi-Fi configuration that you need to connect to. You can reset this in the field easily, connect to it via its AP mode and with your phone or computer, and reassign the SSID and password in the field, and it'll reboot and connect automatically. And then you'll be connected to whatever other network you'd like to be connected to. Yeah, it's built for portability and resilience. It features a light tight enclosure, and it has low power consumption. There's optional 3D printed mounting solutions, so whatever you decide to design. The entire project is fully open source and extensively documented, so you can check out all of that in the links that I have in the description. So if you're interested in building it or just want to get more information about it, it's available for you to take on and customize, improve it, make it your own. The whole system is composed of two main software components. The first is the FlatAF Alpaca, which is a cross-platform ASCOM Alpaca driver written in Python, and it uses the Alpaca framework. It runs on any system with Python 3.7 or later, including a mini PC or a Raspberry Pi or the main capture computer, and it communicates with your capture software over HTTP. The second is a FlatAF MicroPython, which is what is in the device here itself, and it's a firmware stack running on an ESP32C6 board, so that's what's inside that enclosure. And this uses MicroPython. It controls the LED brightness and power through PWM circuit and MOSFET, and it communicates with the driver across your Wi-Fi network. Once both software components are installed and connected on the same local network, they use dynamic discovery to find each other automatically. So there's no hard coding of IP addresses or manual pairing. None of that's required. So for field use, FlatAF supports dynamic networks such as, I like the portable GLINet router, and I'll have a link in the description for that, or even a direct Wi-Fi access point mode where it's needed. It's designed to function smoothly in both mobile and fixed observatory environments. So your control options are designed for both automation and convenience. In a typical setup, you'll run automated flat sequences through Nina's Flat Wizard, for example. FlatAF dynamically adjusts panel brightness in real time, enabling consistent and fixed exposure calibration, which is especially helpful when matching with dark flats. However, the system is flexible and it can just as easily be used for fixing or for using fixed brightness and variable exposure workflows, which is ideal for those who prefer to use bias frames. Manual control is equally accessible, as we've been using here, to make brightness adjustments from any device on the same network. And the onboard button, as we showed, allows you to toggle the LED on or off with just a short press. So as I showed, a 5-second long press enters Wi-Fi setup mode, or the AP mode. And this is where you can go in for configuration and simply enter your Wi-Fi SSID and password for your credentials and stored on the microcontroller here, allowing you to connect seamlessly. You can reset the credentials at any time by another long press of that onboard button. It allows you to easily switch networks whenever you need. FlatAF is designed to be manually placed over the telescope objective and removed by hand. This is an intentional choice for me. It eliminates the need for motors or mechanical covers. I don't want to have a large device like this attached to the telescope all the time, especially with the SCT. If this were a smaller device that was being used maybe on a smaller objective and it wasn't such a large, objective lens, I might actually build the opening and closing mechanism for this, which it certainly could be. Those are built into the ASCOM software and could be written into this device as well. So if you're building one from this model and wanted to make a smaller one, you could certainly add on the opening and closing, the cover calibrator open and cover calibrator close functionality into this device so that it would open and close for you. I just wanted to keep it lightweight, and this allows the design to be battery powered and remain as compact as possible. So this is particularly well suited for my mobile imaging setups and semi-permanent backyard observatory, which I have. Flexibility and ease of use are essential. So basically, I can just run out, put this over the objective, run my calibration frames, be done with it, take it off, and that's all I need to do. It's not really a big deal. So the goal with FlatAF was to build a calibration panel that operates as seamlessly as commercial hardware while remaining open and customizable and entirely DIY. So by prioritizing practical performance and user-friendly integration, the system supports both fully automated and manual workflows. So whether you want to automate a complete flat sequence or quickly trigger calibration from your phone, FlatAF adapts to your imaging style without adding friction. So I want to jump into a demo here. We can jump over into Nina, and I'll do a demo of features and show you an automated dynamic flat session. Over here in Nina is where I'm controlling the FlatAF flat panel device now. As you can see, I'm connected. If we do a disconnect, we can take a look here and see that we've got the ASCOM Alpaca driver devices here. This shows up 137 on this one because that's a different IP that I was on when I was traveling. And then either this 199 or this home 127.0.0.1 works. I tend to use this home first, but while we're here, we can go ahead and click on the settings icon here, and that'll open up the FlatAF welcome page. There's really no settings here in this, but I do have links here to the YouTube channel and to my website. So if you want to get hold of me, you can head over to my website from this link in the driver and contact me via my contact page. If we go ahead and close this, we can go ahead and click on connect here. So we're now connected to the FlatAF device, which is actually currently outside on the telescope. And I'm in the studio, so we're just connecting via remote desktop connection. What we can do, so we're not seeing the actual light right now, so we can just look. But so right now, the flat panel light is turned off we can toggle that on, and that's turned on now. And you can see that the current brightness is 32,767. Right now, that's what I have set for the max brightness, but I can change this in the driver, which I actually am going to, because I found that I wanted to raise this up a little bit for my longer exposures. For my sulfur 2 require a little bit higher, so I'm going to raise this up. I was controlling this to make sure that it doesn't get left at a high brightness level. This is 50% of what it's capable of as far as brightness is concerned. With that, we can go ahead and toggle that off again. So we have the name and the current driver version, which is version 0.0.3-beta. And again, the light is in an off position right now. We can control the brightness, and you can see the range of brightness here. That's determined from what the settings I have in both the device and over in the Alpaca driver. And then over on the right-hand side here, we've got the Flat Wizard trained exposure times. So this is really great. This is part of Nina and the ASCOM, but it automatically saves settings for the trained exposure times. And so, as I'm looking for different filters here, we can see that I'm looking at 2-second exposures for Lume, red, green, and blue. And I go with 4-second exposures for S2, HA, and O3. So those are automatically set up for me. And then my brightness levels are already saved for me too. So these will be recalled whenever I run a flats calibration. If we go over into like the Flats Wizard, this is what I usually use. We'll run a test here. So Flats Wizard will just be the name of it. And the wizard mode, I use dynamic brightness, but you can use dynamic exposure. I like dynamic brightness because that lets me use a dynamic brightness for a set exposure length. That way I can take flats that match my dark flat library. I usually go into multi-mode here. And as you can see, I've got all of my filters set up, and we'll just do one of these. So I've got my luminance is set up, and we can turn it on. And 2x2, 2-second. And I usually go for 40% for histogram mean target with 10% tolerance. So my minimum brightness on this is 200, and my maximum is 1,000. Will come in somewhere in there. I kind of refine these as I go, but this gives it a range to work with. And then I'm going to head over to my imaging tab because I want to connect my camera actually to the equipment tab and camera, and I want to connect the Artemis M Pro. And we'll start the cooler on that. Okay. And I want to start the filter wheel. All right. I'm going to change that to the luminance filter, because that's the one that we're going to do. It would automatically do that anyway. And focuser, we'll need to have that connected. I think that's all that we need to have connected in addition to the flat panel to do some flats. So if I go over back into the imaging tab, we can see here, I'm going to wait a minute. I'll be back because I do want to have the cooler temperature be at -10. Cooling is currently on, so that's going to take a minute to do that. And so I'll be back in just a moment. And we've reached temperature. We're almost there. And yeah, letting it stabilize. But okay, we can go back over to the flats, and we're just going to run the illuminance. And so what we'll be looking for here is our ADU here on the histogram. We'll be looking for about 40%. And then you can watch the bottom along here for our exposure time and the brightness level. So what's going to happen is the exposure time is going to remain static at 2 seconds, and the brightness level is going to update automatically based on what the ADU is. It usually catches this pretty quick. It might even get it on the first try since I have the trained exposure times here, but since I have the range, we'll see. But this is supposed to come in about 225, so we'll have a look and see where it actually starts. And so we'll go ahead and tell it to go ahead and run. So I've got it set at 50 exposures here, which is fine. That gives us a chance to look through these. So brightness setting at 600 to start with. It's going to be too bright. And then it's going to dynamically adjust the brightness of the flat panel. So it's down to 400 now for this exposure. And we can see that our ADU is coming down. Now it's on 300. Okay, we came down again. We're going to get down to that 250. That's where that saved setting is. This should be close. So that's 50. It's probably going to drop down just a little bit more. Okay, that should put us in the 40% range. Okay, it's taking exposures now. So we're a 4 out of 50. So things to look at here. So I do have a little bit of vignetting, and I do have a dust mote here. I've had this for a while. It's time to clean it off. I finished my current target. My current target, I was going to crop way down inside here, so I didn't care about that corner anyway, and everything else is clean. I didn't want to take the scope apart, the image train apart to clean this when it didn't really matter for my project anyway, so I just let it be. And it does actually calibrate out with flats. Now you can see this is so nice and smooth from the flat panel. There's there's no artifact or anything like that from the panel itself, or any type of graininess or anything. There's no flicker, and it does a fantastic job on here. These flats, when matched with my dark flats, they've done just a wonderful job of calibration. And I think one of the main things about it is that I'm able to take these longer exposure flats now, and that helps fill up the well on the sensor pixels so that I get a lot more signal in for my calibration frames, and that really seems to help a lot, and it's made a big difference in my final images. So we can go ahead and let this run out. But yeah, back to here. Okay, it finished. It did all 50, and that's basically the demo. The flat panel, it's really simple. There's not a whole lot going on in controls. It automatically shut off there. It didn't disconnect, but it set it to 0 after we were done, and that is intended. If I ran another filter, it would go ahead and it would turn back on to whatever the desired brightness is, per our configuration over here in the trained exposure times, or for the Flat Wizard. That's the demo, and we'll go ahead and go back to the main video now. All right, so how can you get the code? So FlatAF is fully open source project released under a permissive license for personal and non-commercial use. Organizations who are interested in using FlatAF software for commercial flat panel products are encouraged to contact me over on my website to discuss licensing opportunities. So everything required to build, program, and deploy your own FlatAF system is available on my GitHub and on my website. And this includes the full ASCOM Alpaca driver written in Python using the Alpaca framework, the MicroPython firmware for the ESP32C6 microcontroller board, and setup instructions for both components. The repository also contains detailed documentation to guide you through every step of the process. You'll find a PCB diagram for connecting hardware components and guides and flashing the firmware onto a microcontroller, and instructions for deploying the Alpaca driver to your imaging computer. In addition, the repo includes pre-configured Postman collections for API testing. You'll find links to download the design files in the description. You can explore or download, clone the code at the FlatAF GitHub repository. So what will you need to build it? I have a whole list of things that I recommend. So building FlatAF is rewarding, and it doesn't require a whole lot, but having the right tools and components on hand will make the process more efficient and enjoyable. So I want to outline, the essential stuff here. I've got a bill of materials that's available. You can get to the bill of materials over on the GitHub. Some things that I recommend, that you should have that can significantly streamline the build process and make it more enjoyable. You may already own these tools, but if you're just starting from scratch, these are fairly affordable beginner kits available online. So here's some following items that I might suggest. I got an Xtronic 3060 Pro solder station, and honestly, this was the nicest soldering station I've ever had, and I really suggest it. And it is not expensive, and I think it was just fantastic. You're going to need some rosin paste and some soldering flux. You'll want to get some solder wick in case you have to take some things apart. If you're like me, and I'm not really great at electronics, I had to go through this learning process, and I did put things together and have to take them apart again on multiple occasions. So having what you need in order to remove components from the board can help you and potentially save some money and rework. Makeronics 1660 solderless breadboard is fantastic, and it comes with a bunch of stuff that you can use in the project, like resistors and stuff like that. So that, and the model that I had came with its own power supply. It was so useful in prototyping everything and testing before I actually even started building the enclosure and putting this all onto the PCB. It also helped me design and understand how to design the PCB when I got to that point. And then, like a good wire stripper, your self-adjusting wire stripper, that will help you out a lot when you get into wiring into the enclosure. So these tools are not exclusive to FlatAF, and it can probably serve you well across a wide variety of electronics projects. So if you're a hobbyist and into this, then it won't be just a purchase just for this project. You'll be able to use this for, these tools that I'm suggesting for lots of different things. So the bill of materials, again, you can build FlatAF for, it's actually, I did it for less than $100. I have that listed. And I provided a table over on the website that lists, on the companion blog post for this video, that lists all the core components used to build FlatAF, which includes links to the purchases and an estimated prices at the time of the original build. So these are the exact parts used in the working prototype, unless otherwise noted. So networking and control recommendations. A little bit of a rant-ish here. So although Windows can technically create a mobile hotspot, I do not recommend it for astrophotography applications. The Windows hotspots suffer from several limitations that negatively impact wireless network devices such as FlatAF. Most notably, Windows assigns connected devices to an isolated subnet, so typically like a 137.x subnet, which prevents proper UDP broadcast and breaks dynamic discovery for ASCOM Alpaca devices. So additionally, hotspot behavior is often inconsistent following system sleep or reboot events, and there's no reliable method for assigning persistent IP addresses, which complicates automation, file sharing, and remote control workflows. And this compounds the issues where many consumer routers experience problems with UDP broadcast between 2.4 gigahertz and 5 gigahertz bands. So this device and others like it communicate on 2.4 gigahertz. When those broadcasts can't be mapped across to the 5 gigahertz bands, within your network, then that can disrupt the discovery and device communication across mixed band networks. For a more robust solution, the recommended approach that I give is to use a dedicated travel router. One excellent option is the GL-iNet portable router. I have a video on this. I'll put it up here. So the GL-iNet creates a stable self-contained Wi-Fi network that functions reliably both online and offline. So this setup allows all devices to share the same subnet, commonly, usually be like 168.1.x, ensuring that UDP broadcasts for Alpaca discovery are not blocked and DHCP or static IP reservations remain consistent from network to network. So in a typical deployment, the FlatAF panel connects to the router, and it's controlled over the Alpaca API by an imaging computer running Nina or other device, driver software, and the FlatAF Alpaca driver itself. A third device, such as a laptop or tablet, can connect via remote desktop, which is the way that I do it, or similar protocol to operate the imaging software. So this architecture allows seamless control, dynamic discovery, and fully automated flat frame sequences, even in completely offline environments. So you can grab the FlatAF device firmware and ASCOM Alpaca driver files from the FlatAF GitHub repository. And again, that link is in the description. And the FlatAF device design is a fully 3D printed system, and all parts are available in editable formats for their designs to support modification, remixing, and customization. So this was my first major Fusion 360 project, and while I did my best to implement parametric design, the flat panel itself is only partially parametric, and the enclosure is much more, I did a much better job on the enclosure for the electronics than I did on the panel part itself because I started with the panel. But I had learned a lot more about Fusion 360 and parameterization as I moved through it. So anyway, I went back through and I redid a lot of the parameterization on the light enclosure part. But then I did pretty good, I thought, on the microcontroller and battery enclosure part. And so I think you'll find that it is possible to change the dimensions of this. However, I think that you will find there's going to be some work involved in doing that, but it should be possible. And you may want to just design your own enclosure and go your own DIY route, which is totally practical, thing to do. And then you can just use the software for the device and the driver, and that'll work perfectly for whatever it is that you want to DIY. So there's no rules. You don't have to use the design files. You can use the device microcontroller and the Alpaca driver together. Those two need to go together because they're built together. And then use them with any device that you'd like to load that microcontroller on. This design was built specifically for the Celestron Edge HD8, and I haven't tested it with any other 8-inch OTA. The dimensions and tolerance may require adjustment for other tubes. Additionally, your printer's calibration and filament type and material shrinkage may all affect their final fitment, and my process involved printing test sections and making iterative revisions and tuning the printed settings as was needed. So, and due to the size of the panel and the build volume of my printer, I split the panel into two halves, which I can show you. So there's actually a seam here. And then I created a sliding dovetail joint on the edge here. And this may require some light sanding or filing to get the exact fit. Mine did. It wasn't much, just lightly dressed it. And then once aligned, I permanently bonded these two halves together using super glue. And it's super strong. So the light subplate is a plate that goes inside this in the bottom. I made that out of white PETG, and it functions as a gusset to hold it, to help support and the two halves together and make them stronger. But it also is designed in order to be a reflective surface for light that is inside the light panel to help direct and reflect the light from the LEDs ultimately out through the diffuser. So anyway, to wrap up, I've used FlatAF exclusively on my Edge HD over the past several months in testing and in what has become every session use. I used it both at home and under dark skies while traveling. It has quickly become one of those tools I can't imagine going without now. The reliability and the simplicity, the flexibility it brings to my flats and workflow has fundamentally changed how I approach calibration in the field and here at home. For traveling, I put together a really nice backpack bag to safely travel with FlatAF, and I'll put a picture of that up here. If you'd like to support this project or decide to build one of your own and need a case for your FlatAF flats panel, please consider picking these up at the official FlatAF Backpack in my store. I've got a link for that in the description. So I'm proud to release this to the community, and not just as a utility, but as a jumping off point for creativity and customization, and to give something that I've enjoyed building back to the community. And hopefully it will be something that you find fun and enjoyable and helps you with your workflow. So whether or not you want to improve it, remix it, miniaturize it, add new features, you have full access to do so. And that's the spirit of open source and sharing tools that are practical and hackable and built to evolve. I hope that you've liked this demo and my introduction of FlatAF. I'm really have been excited to get this out, and it has been such a long time coming. The project, when I got into it, I really didn't think it was going to be a 6 to 7 month project to get to this point, and it became much bigger for me than I had anticipated. So I hope that by releasing this to the community and in basically a ready to go form could save you months and months, of work in creating your own flats panel for less than $100, and have software that already works with ASCOM. With that said, I hope that you'll check it out. I'll have a section over in my DIYs on my Discord. Link will be in the description to my Discord server. And I'll be posting some things over there about the DIY build here for this and other projects as well. And so please, I invite you to join over there. And if you'd like to support my channel and my content, I would love to have you as a channel member. And you can join as a YouTube member. I also have a Buy Me a Coffee. You can join a membership there, and that gets you access to perks no matter which way you go, and also to members-only chat over in the Discord. All right, so my name is Doug. This is AstroF. And thank you so very much, and I hope you enjoy FlatAF. Flat's so smooth you could calibrate your life choices.